Hello everyone, welcome to my channel. My name is Adam and I'm from Morocco. Today I have a difficult elementary geometry problem for you that I have got from my maths textbook. So here is the problem. I've drawn a rough picture, but here we have a right angle triangle and a square inscribed inside of it. From the vertex of the square to the hypotenuse, we draw two more squares outside of the triangles. If we label the surface area of this big squares S1 and the surface of these squares S2, the surface of the original squares S3, then the question is prove that 1 over S1 plus 1 over S2 equals 1 over S3. Give it a try, and when you're ready, keep watching the video to see the answer. So, how are we going to solve this problem? Well, since the problem is about the areas of squares, why don't we recall the formula for the surface area of a square? The surface area of a square is nothing but its side length squared, right? This is basic. So if we want to apply that to our case, we have three squares. Let's start with S1. So S1 would be the surface of the square ACBI. So ACBI. And what is that? Is the side length AI squared. Likewise, for area S2, which is the area of square DFIE, and this equals this side length EI squared. S3, which is the surface area of IJKL, is equal to a side length, like I'm gonna pick IJ, so it's IJ squared. So the problem of 1 over areas has now become prove that 1 over IJ squared equals 1 over AI squared plus 1 over EI squared. So now we can rephrase the problem that we originally had as to prove that 1 over IJ squared equals 1 over AI squared plus 1 over EI squared. So how are we going to prove this formula? Well, let's take a look. We have AI squared and we have EI squared. If we take a look back at our shape, AI is the leg of a right triangle, which is right at this point here, L. So, since it is a right angle triangle, we can use the Pythagorean theorem, which says that the hypotenuse AI squared is equal to the sum of the squares of the two legs, AL squared plus IL squared. But this IL here, this is a square, so all of its sides are equal. So IL is in fact one and the same as IJ. So we can change that. We can write AI squared instead as AL squared plus ij squared. And the same thing is true for EI. We have a right angle triangle at the point J. So the Pythagorean theorem says that EI squared equals EJ squared plus IJ squared. So now we have turned the problem from finding a formula that links IJ, AI, and EI to IJ, AL, and EJ, since we have an IJ here and here. And so what we really need is a formula that links these three side lengths, IJ, AL, and EJ. So what could this formula be? So to find the formula that links the side lengths IG, AL, and EG is a little bit tough, but we need a careful look back at our shape. So if we take a look at AL, EJ, these two belong to two right angle triangles, and so maybe these triangles are similar. Is that true? Well, we can check. Recall that to prove that two triangles are similar, we use the angle criterion for similarity. That is, if two angles from one triangle equal two angles from another triangle, then the two triangles are similar. So here we already have one angle that is the same, and this is the right angle, here at J and here at L. We need to find two other angles that are the same. Let's think about it. So IJKL is a square. Therefore, here we have a right angle. And here too we have a right angle. So in fact, IJ and AK are both perpendicular to EK, which means that they are parallel. And since both of these lines are parallel, IJ and AK, and this other line, EA, crosses both of them, then it does at equal angles. In other words, this angle here, EIJ, is equal to the angle IAL. So we have fulfilled the angle criterion for similarity. So here I've written out what I just said. We started with the two angles who were both pi over 2, were both right angles, and the two parallel lines IJ and AK, because they were both perpendicular to the third line, EK, and I showed that this gave us the two equal angles here, these two angles between these two parallel lines and this line that crosses both of them, and I showed that these two and these two are enough to use angle criterion for similarity and get that the triangle EIJ is similar to the triangle IAL.